Welcome to Chapter 11, Part 4, Principal Component Analysis, PCA. In this section, we will explore PCA, a useful dimension reduction technique. Let's get started. In many real-world situations, we may encounter data sets with a large number of variables referred to as high-dimensional data. Sometimes the number of variables even exceeds the number of observations. While we may eliminate some redundant variables, dropping variables might result in losing valuable information. Principal Component Analysis, PCA, is an effective dimension reduction technique. It transforms a large number of possibly correlated variables into a smaller number of uncorrelated variables called principal components. These components summarize the data with fewer representative variables, collectively explaining most of the variability. PCA is considered an unsupervised data mining technique. It allows us to select a small number of principal components that drive most of the patterns in the data. PCA can be used to visualize and pre-process data before applying other unsupervised learning methods, such as clustering. It can also be used with supervised learning methods like linear and logistic regression. The principal components, PCs, are weighted linear combinations of the standardized original variables. The weights are derived using an eigendecomposition. The first principal component accounts for the most variation, the second for the second most, and so on. If we had k original variables, up to k principal components could be constructed. PCA ensures that all resulting principal components are uncorrelated while capturing almost all the information in the data. Let's look at an example using JASP. Open the 11.36 data file and save it as a CSV format in your Downloads folder. Upload the file into JASP by navigating to Open then Computer, then Downloads. To run PCA in JASP, go to Factor, then Principal Component Analysis. Drag X1 and X2 over to the Variables box and select the settings as depicted in the screenshot. Compare the model results with the book answers. Using the covariance decomposition, the first component explains 86% of the variance. Using the correlation decomposition, the first component explains 85% of the variance. Therefore, the two variables can be reduced to a single principal component. The mth principal component for the ITH observation is calculated using the formula presented on this slide, where WMK is the weight for the KTH variable of the mth component and ZIK is the standardized value for the ITH observation of the KTH variable. Using the data below, compute the second component score for observation 2. We can see the result is 0.862 for the second component of observation 2. Thank you for your attention. This concludes our discussion on principal component analysis.